Okay, so for Chapter 8, we're only looking at two sections. We're looking at 8.2, which is integration by parts, and 8.7, which is L'Hopital's rule. So integration by parts, and basically if we're trying to integrate something and we're multiplying by two pieces and we cannot use U substitution, it's just not going to work. We've got a rule that says if I can split them up, and I've got a U piece and a dv piece, I can take the antiderivative of dv, take the derivative of du, and then I can rewrite it. I just went blank. V du. Yeah, I was like, that doesn't look right. So V du. Okay, this is supposed to be a V. Okay, then we can try to take the antiderivative of it. So an example would be, so say I had x cosine of x dx. So there's nothing that I can let u be that's going to really change anything. I can't let u equal cosine because sine's not involved. I can't let u equal x because u equal x is kind of silly. So what I'm going to do is set one piece equal to u, one piece equal to v. Now I want to be able, if I let u equal x here, now take the derivative, x goes away. Now let's let dv equal everything else. Let's let it equal cosine of x dx. So if I take the antiderivative of cosine, I'm going to get sine of x. Okay, so now, we're just going to stick in. So if I rewrite this, it's going to u times v, so I have x sine of x minus my v du, sine of x dx. Now, this is pretty easy. That's not anything weird. So what is the antiderivative of cosine? It would be what's the antiderivative of sine? It's negative cosine. So I've got x sine of x minus a negative cosine, so it's plus cosine of x, and then we have our plus c. And that would be our answer. So let's look at another one. So what if I had arctangent of x? Now if I remember from back in Chapter 5, we found how to take derivatives of arctangent, but we never really had any antiderivatives that were just arctangent. And we really don't have anything else in other pieces. So what I'm going to do is let u equal arctangent, and then dv equal dx. And let me slide that over because my paper is off center. So I'm going to take the derivative here of arctangent, so it's going to give me dx over 1 plus x squared. The antiderivative of dx is just x. So now I'm going to have my u times v, so I've got x arctangent of x minus my v du. So I've got x times this. Okay. Now, that looks like a mess, but it's really not bad because if I'm thinking u substitution, I can let this equal u, and my derivative, so I've got x squared plus 1, my derivative of that is 2x dx. Okay, don't let it confuse you that I'm using u here and u here. They're two separate pieces. This was for the first one, and this one's for the second. So I don't have a 2, so I'm going to move that on front. So I've got 1/2 du x dx. So now this, I've got x arctangent minus 1/2. This is my du. This bottom piece here is my u. So that is natural log. So I've got natural log of u, which was x squared plus 1 plus c, would be our answer. Okay. So let's look at one like this. All right, so say I have that e the negative 3x sine of 5x dx. Okay, so if we have e to the x's and like a sine or cosine that are going to, both of them are cyclic functions. They just repeat after repeat after repeat. because a lot of times we're going to try to, if you have an x squared or an x, you want to let that equal u, because when you take the derivative, they get smaller and kind of go away. In this case, neither one of them ever go away. So what we're going to do is let u equal our trig function, and then my dv equal my exponential. And that's dx. What is that, a 3? Yeah. So my du is going to give me cosine of 5x times 5. My v is e to the negative 3x, and then I'm going to have negative 1/3 in front of it. So when I rewrite this, I'm going to have these two. So I have negative 1/3 e to the negative 3x sine of 5x minus these two. A negative 1/3, so it's going to make that a plus, e to the negative 3x cosine of 5x times 5. I'm going to go ahead and put that 5 out here. Dx. Didn't really get me anywhere. So let's do it again. So we're going to do the exact same thing again. So I'm going to let u equal cosine of 5x, and then e to the negative 3x dx. So this is going to give me negative 1/3 again, e to the negative 3x. This one, going back, no, I'm taking the derivative. It's going to give me negative sine of 5x times 5. Okay, so now let's rewrite this. So I'm going to start with my original. So I've got, this is my original. That equals this piece here. So x plus 5/3 times, then here. So I'm going to have these two. So negative 1/3 e to the negative 3x cosine of 5x minus these two. So I've got negative 1/3, negative 1, so it's going to stay negative. There we go. It's going to give me e to the negative 3x sine 5x. Oh, and I've got a 5 here, so I'm going to put a 5 there. Okay. I want you to see something. Oh, and you can't see any of that. I have it all. There we go. So we rewrote it. So we started with the original. So we rewrote this piece, then 5/3, and then the antiderivative of this. So we've got u times v, it's here, minus the antiderivative of v du, so these two. So we took my 1/3, took my 5, and moved it up front. Notice I've got this piece here, and this piece there are the exact same. Okay, so now we're basically, that's what we're solving for. So we're going to treat it like an algebraic expression. So let's see, so I've got, let me go ahead and distribute all that. So I know what my constants are. So that's a dx. We've got negative 1/3 e to the negative 3x sine of 5x. Distribute, that's going to be minus 5/9. You get the negative 3x cosine of 5x. And distribute those, it's going to give me negative 25/9 integral. And same thing. So if I add this over, so I've got, this is 1 plus 25/9. It's going to give me 34/9 of this is equal to this. Okay, so now all I have to do is divide by my 34/9. So my answer would be 9/34 times this. And so that's about as ugly as integration by parts gets. I mixed a lot of them. So if you can do that, you can pretty much do any of them. So that's about as ugly as they get. Okay, now L'Hopital's rule, it's nice. It's actually pretty nice. It's talking about limits. So we're talking about limits, and the rule tells us that if I end up with a 0 divided by 0, or infinity divided by infinity, or any combination of that, so those are considered indeterminate, then what we can do is take the derivative of the top, take the derivative of the bottom, and the limit is the same. So these two are equal to each other. Okay, now do not let this confuse you with your quotient rule, Okay, we can't do that with quotient rule, just take the derivative of the top and bottom. But for L'Hopital's rule, we can. Okay, so if I have something that looks like this, I've got the limit as x goes to infinity of e to the x over x squared. Okay, so I have this. Now if I plug in infinity here, if I plug in infinity here, e to infinity is infinity. It's infinity. X squared to the infinity is infinity. Okay, so what I'm going to do is take the limit of the top and the limit of the bottom. So I've got e to the x, not take the limit, take the derivative. And then here I've got derivative 2x. Now if I plug in infinity, I still get infinity over infinity. Ugh. So let's do the same thing. So I'm going to take the derivative of the top, take the derivative of the bottom. Now if I plug it in, I get infinity over 2. That is just infinity. So it's saying our limit's undefined because it's going to approach infinity. It's unbounded. Okay, so let's look at another one. So say I have the limit as x goes to 1 of the natural log of x over sine of pi times x. Okay, so if I plug this in, I have the natural log of 1 over sine of pi. Natural log of 1 is 0. Sine of pi is 0. All right, so we've got 0 over 0. So we can take the derivative of the top. It's going to give me 1 over x. Take the derivative of the bottom. It's going to give me cosine of pi x times pi. Now if I plug it in, I end up with 1 over 1. Cosine of pi times pi. Cosine of pi is negative 1, so I have 1 over negative pi would be my answer. So L'Hopital's rule is simply that. If you get 0 over 0 or infinity over infinity, all you have to do is take the derivative of the top, take the derivative of the bottom, and then plug it in and see what it gives you. So it's pretty nice.